we'd like to present real-time and low latency media transport stack based on DPDK. I'm Ping from Intel, and Frank will present the next session for the memory receiver side. Firstly, I will introduce the background for our project, and then I will present what's the architecture and detailed implementation of the project. Finally, we will present the summary for us. Basically, we are DPDK users. We leverage DPDK functionalities to build a media transport library for video production environment. And what's the video production environment? It is basically the front end, the first side of the media production. Take Olympic game as an example. There are many cameras. They shoot the stadium and the venues so that the people can get the information for live broadcast. And the production industry is the front end for the cameras and pass the camera signals to the deliver side and the codec to the broadcast to the audience. And basically, this is take the SDI as the interface. Camera will be connected with SI cables, and then the camera captured will be transmitted and delivered to the central broadcast services. And the STI has lots of issues because it needs a lot of trucks and also people for the renewals. This is very heavy, and now in the future, people are looking forward for edge and private or public cloud deployment of this service. And everything is based on IP. And IP solution will greatly reduce the cost for the production industry. It can also remove some footprint so that there will not be lots of trunks. And it also can be enabled for remote and distributed content creation. And everything is trying this for this. The transmotion is from SDI to IP side. And since the move is from that society and motion picture and television engineers, this is short for SMPTE, is a well-established organization. It has driven these transitions from SDI to IP-based. So since this is IP-based, there are lots of standards we need to qualify. And it reached the ST2110 standard. And ST21 standard has lots of subsuits. There are different numbers. For example, ST2110-10 is used for system timing. -20 is for uncompressed video. -21 is for packet pacing. Packet pacing is to simulate the signal pacings like SDI did, so that it can be used for hardware-based increment. And -22 is for compressed video, 30 is for uncompressed audio, and 31 is for compressed audio. 40 is for the data. And ST22-7 is for the redundant path. It's basically trying to enable 2 ports, and 2 ports will deliver the same content, and the same content will come to the same destination. And in the destination side, it will trying to duplicate this content and recover to the video sessions. And this is the full standard for ST2110. And for the libraries who want to meet for that, and then it can provide the production deployment. To face this change, to face the SDI to IP changes, Intel provides a media transport library. And this library is to provide the fundamental functionalities for ST2110. And it can also provide, help you to provide the video audio and also the data over IP networks. So this is our media transport library did, and to meet for the production transmission from SDI to IP. The features for media transport library is that for the standard compliance side, it provides full ST2110 standard. For example, for -20-21 and -30 for audio kind of implementation for that. And besides the ST2110 standard, there are also some protocols we also need to provide. This is underlining protocols. We provide IGMP. With IGB, we provide multicast transmission so that one transmitter can be delivered to multiple receivers. And we also provide point-to-point deliver. So ARP is also enabled in our library side. And the most important side is that we leverage hardware to implement PDB protocols. These PDB protocols currently is not very mature, but it currently provides solutions to sync time with the grandmaster so that it can got the time. And for the OS support, currently we support Linux. Linux is the platform, and the OS we start from the beginning. And then we also support for Windows. From later, we will also introduce something based on Windows side. Windows side we also based on DPDK, but we also found that there are some features which is not completely compliant with Linux. So we have something to discuss that later. Now for the media transport library, what's the scenario is that it can be run in the bare metal environment, and we can also run that in the edge and the cloud support, so that currently we can enable media transport library in the container side, and we also support virtualization to get the exact timing for this. Yeah. So the reason why we build DPDK is for several benefits. Take the pictures from left. Left is the traditional way that it will go through kernel space. And we can see that there are multiple paths. There are also some copy need to happen. And it will greatly to reduce the latency, reduce the latency overhead so that it will add the cost for latency. And at the right side, we provide DPDK solutions. And based on VFI driver, we can reduce the memory copy, and we also can reduce the interrupt. And finally, we can have a very good streamlined and optimize the stack for this. And DPDK also give us the way that we can access hardware directly, so that we can go and to utilize the fundamental features in the NIC. And so this is also provide us very good and enabling time, reduce our development cycles to achieve that. So let's see the media transport library architecture. What we did is similar like DPDK did. DPDK is a development kit for the packet I/O, and for our media transport library, we also provide some APIs. This is for the fundamental media transport. So this is our fundamental APIs. And these APIs include two parts. One is for the transmitter, another one is for the receiver. And based on the library, we also provide some sample applications so that it can demonstrate how we can use this transport library, just like DPDK did. DPDK also provides some examples for us to know how to use that. Take this picture as an example. For example, for the video side, when the application generates the video frames from the video producer, it can call media transport library. And this library will convert the video buffers to be ST20 sessions. 20 is follow ST2110-20. This is for the uncompressed videos. And this video will be generated as a session, and then we can encapsulate that with the RTP packet, with the timing and with the information how we can encapsulate these sessions. And after this packet is encapsulated, we will generate a packet pacing. This is to adapt to ST2110-21. 21 requires that it need to, for each of the two packets, we need to generate a unified pacings. And to implement the pacings, we leverage the limiting features from NIC. And we also provide the TSC. But the limiting provide a very accurate way to implement the packet pacing. Due to time limit, we will not introduce more information about that. And basically, we just leverage the hardware features to do this packet pacing. And after the packet pacing is generated, we will deliver this traffic to DPDK framework. And then it will go to PNG driver, to VFIO driver, and finally, it will be delivered to the wire. And in the receiver side, we do similar things. When the DPDK framework receives the packet, firstly, the library will do packet classification because there are several different packets. Some is for the data plane, for the RDP, for the video, for the audio, and we will separate them to different sessions. And we also provide IGMP support and ARP support. So we have a dedicated queue which will handle the other supporting protocols such as PTP, such as IGAP kind of things. And we also support user to leverage KNI interface to implement the TCP/IP stack, to leverage kernel to do the TCP/IP stack. So this is also the theme. We provide the utilities so that user can do this job even if the interface, the NIC VF or PF is controlled by DPDK, but it can also leverage kernel space to do some similar things. We also have some things we did in Windows because Windows do have the KNI, so we have to leverage the tab device to do this job. So this is basically what our media transporting library did and how we can implement that. And to implement that, we realized that synchronized is very important. For example, for one session, there are several stages. Firstly, it needs to do the encap, for example, in the transmitter side. And after encap, it needed to be transmitted to NIC to do the limiting, to the packet pacing. And after that, it also needed to go through the DPDK framework. So for one sessions, there are different pipelines. And then how to organize that, we implement something, we call it as a scheduler. Scheduler is the main scheduler, is to schedule Tasklet. And Tasklet is one of the portion of the pipeline. For example, if for session 1, we have several different stages. So we separate each stage as a tasklet so that this tasklet can be called by scheduler. To apply this job, you can see that from the right side, we will have a mechanism. For each of the tasklet, it will be registered from the scheduler. A scheduler has this information, and it will dispatch the tasklet one by one so that it can be run. This is very similar, like a graph concept in DPDK, also like in other projects like we did. But Tasklet is defined by us, and we can just provide a very simple way how to organize different stages of the job and how to separate the job into different stages. Then we can provide synchronized solutions for that. And with this design, we can fully utilize CPU resource because we can imagine that for in different stages, the tasklet will do different jobs, and some might do waiting for I/O. And so this tasklet is running other tasks when this is waiting for I/O event. the scheduler can switch to another tasklet so that we can further utilize the CPU resource. And by this way, we can, because all of the tasklet will be handled in one CPU, so we could provide a very good data affinity. So this, everything will be running in one core for one job, so that there's no core-to-core extra cost. And because we also realize that for each of the for the media transport side, the timing is very important, and it is very sensitive to timing. So we provide a predictable time for us for each of the tasklet, so that we know that definitely one tasklet will be run to avoid a long time waiting. And this asynchronized architecture can help us to do to integrate that with accelerators. For example, we leverage DMA dev to help us to do memory copy, and this is basically to send out requests to the hardware, and response will come in later, right? So in this way, we can separate the tasks, the main job, request, and response to different stages, so that it can be easily to be integrated with accelerators. So this is our tasklet-based synchronized architecture. So from the software stack perspective, we will separate our whole structures into two sides. One is the control plane, another one is the data plane. And the control plane is to management sessions, manage the scheduler, and also this can also be used to manage pacing. We will use that to train and pick up the limiting bandwidth, so that we can provide a very accurate packet pacing according to ST2110-21 standard. And control plane will also to set up a device and to allocate resource for each of the sessions. And for data plane side, we provide the media transport, and we provide the receiver side and the transmitter side. And the transmitter side, we have two stages. One is that we do packet encapsulation, and we also provide the pacing. And the next side is also to transmit to the NIC. So we talk with NIC, and even if NIC sometimes will tell us that it has no enough space, but we will continue to transmit until the first stage, the pacing, the packets will be delivered to NIC based on the asynchronized tasklet. And in the receiver side, we will burst from NIC, and then we will do classification, and we will do like decap, decap, and then finally deliver the frame to the application side. And for the underlying protocols, we also have a tasklet which will manage the ARP, manage the IGMP, PDP, and this protocol will provide service for the data transmitter and for the data receiver. So this is our software stack for the media transport library. And actually, we have enough job to do. We have many implementations. So due to time limit, I will not cover 4 of the features. But we will, here in this presentation, we will just pick up the most important sections for introduction. We will focus on the memory side. As we mentioned that DPDK provides a very good scenario for memory copy. So, and we realize that DPDK can provide us hardware access, so that we can provide SGL interface. So based on this, we implement a feature so that we can implement the other copy. Basically, you can see that for the video frame, it is very big, and it is pretty big. For example, for 1080p 60 422 format, one frame contains about 5 mega. So it is pretty big, and this just happened in one of the frames. So there you can imagine that there's a huge memories, and to reduce memory copy, what we did is that we leveraged the DPDK external buffer, and we put the video frame into DPDK external buffer, and then we will allocate M buffer. This M buffer we will use just for the header. And based on this buffer, we will fill the UDP header, we will fill the RTP header, and then we provide another M buffer. And this M buffer will leverage external buffer interface so that the two buffers will be linked. One buffer provides the header, and another buffer provides the video frame, one portion of the video buffer, so that we will submit the chained M buffer. One is the header, another one is the payload, together to NIC. And most of NIC support SGL interface, so that we can provide a to address to NIC, and NIC will help to form the last RTP package and deliver that to NIC. So based on that, we can implement the zero copy in the transmitter side. And for receiver side, we also have some features. Frank will provide more information about that. Frank, it's your turn.你 mute 了。
Sorry, my mic is mute. Sorry. Okay. Thanks, Ping and Frank, software engineer from Inter-China site. So it's really an honor for me to be here to talk about the topic on the low latency, real-time, and reliable media transport library based on DPDK framework. So I will continue to talk about the receiver function detail, use the DMA to offload the memory copy, and furthermore, use NIC head split feature to save the copy to reduce the memory bandwidth usage. Also, I will talk about the support status on Windows platform and the issues we get. We probably need the community help to find a solution. Windows is really important since most current video production framework and the video production platform is based on the Windows solution. So, okay, for RX process, the first step is to set up the RTE flow according to the IP address and the port number and other necessary info. So after the RTE flow is or the packets classification is working, then we call the RxBest API to receive the packets from NIC. So the final step is to decouple the head info in the packets and copy the payload data to the frame buffer address. So and notify the user application if one complete frame is received. So we are inspect the head info detail. Since our design is based on the Tasklet model, we can submit the memory copy operation to the DMA hardware engine and finish current packet processing. So in next Tasklet running time, we call the complete API to query if the DMA copy is done or not. And if the copy is complete, then we can free the M buffer to the memory pool. So with the flexible Tasklet ways, we can fully release the DMA hardware capacity. Our benchmark shows we can double the performance data if we use the DMA offload. So, okay, next page is the head split. So head split is one hardware feature. So modern NIC like Intel CVL, the 800 series has this support. So we use this feature to save the copy of video data. So NIC has the function to analyze the packets by the DTP firmware according to the programmed rules. Then the hardware will help to split the head and the payload into different locations. So from software side, we can program NIC to place the payload data to our video frame buffer directly. Then we can save one copy in the software. So this is here is our current software solution for head split. So first thing we do is to enable the feature, the head split feature in the PMD and the ETH device layer. So and the path is upstream already. It's in upstream. So but then we create external memory pool which presents the frame buffer. So one major issue or challenge is that usually the video buffer, video frame buffer is really large. For example, for 8K frame, so 8K resolution it need more than 100 megabytes. So the payload memory pool need nearly about 2,100 M buffers to hold all the video data. So which is really crazy number, and it had the performance badly. Our profiling shows it can reach about 60% last level case miss ratio. So sounds like a very bad data affinity case. To resolve this problem, so we develop a new memory pool type which the I/O address is assigned at a long time instead of current static assignments in the M buffer creates routine. So for our case, we can set up a memory pool with only 2,000 M buffers, and we dynamic resolve set the IOVA address in long time. So with long time IOVA mapping, so this approach give DPDK users the full control on the package IOVA address at a long time. So it's very flexible and powerful, and it's working well in our case. And our performance data shows it can only one L core can handle all packets processing for one HK session. So it's about 40 gigabytes traffic only in one core. So later we will work with the community for one stable API and the detailed implementation. Okay, here is the Windows support status for our solution. So most key feature is support as Linux already. Our Windows solution shared some code base with Linux, only very small difference. So, but anyway, we fixed some small issues like the P thread, which is a Linux API, and the Luma issues, and some cute page issues and some small bugs in the Java side. So we can get similar performance data with the kernel bypass UL Java, but we still meet many tough problems for Windows. So the first is Windows only supports UL Java right now, so no SROIV based web support. So as you know, all our users are on the road to the virtualization from the bare metal only. And the second issue is low CNI support for Windows. So, but we develop a very similar type of solution. And the third is the Qt page support. Windows only has 1 GB page now in the Windows 10 version, and so it doesn't have the 2 MB page now. But most of our case is wants to use the 2 MB page, and the last but not the last is the VFile or IMMU support in user sports. Windows doesn't have the VFile framework nice now in the user space. Okay, this page shows the Windows type Java detail. So our type solution is based on the OpenVPN side type Java. So it's when we get a packet from the network, we first check if it's the ST2110 packet. If it's not our packet, we forward it to the NDS block, and that other application can receive the packet by the APIs. So when there is a packet sent by other application, we can query the NDI API to get the packet, and the best is to the network use DPDK TX best API. So the working module is very similar to the Linux KI module, but we get some performance issues which is still in the fighting stage. So with the type Java, the normal network packets can route to the OS TCP/IP stack, and both the traditional application and the DPDK based application can use the same port, the same NIC ports. So Ping, this is my part. Now your turn again.
Yeah, we can provide the summary for our presentation. Firstly, we provide Intel Media Transport Library takes advantage of DPDK features. We implemented highly efficient and real-time low latency media transport stack. So most of that is leverage DPDK's fancy features so that we can access NIC directly. And this is the more important thing we provide. And the second is our media transport library is totally by COTS hardware, and it leverage hardware. We are not dependent on specific hardware. So now industry is mostly use the specific hardware. So it will make it difficult to go to the cloud. So our software solutions is make it available for the edge and the cloud deployment, so that more people can leverage this. And based on this media workload, we also enhance DPDK. As we mentioned that we do something in a packet paging. This is in the traffic management component. And we also trying to enhance PTP library, memory pool enhancement, and we also trying to upstream more features for hand split. So that's to make this workload to be one of the component, one of the advanced features in DPDK. And we can also leverage these features to make a DPDK to have enhanced features in the future. So thanks. So last page. Yeah, I'd like to take this chance to thank many team members. From Rao is our project architect, Jin is our validation engineer, engineer leader, and Chao spent my time to Windows platform enabling. Ming is the project engineer, Rajit and Palef, and help us to address Windows DPDK issues. Xuan help us to do DPDK hand split features for upstream work. Yeah, thanks all for the contribution in this project. Okay.
And I believe we have Frank and Ping live here on the Zoom. Hi there. Ping, are you able to hear us? Can you hear us? If he has sound. Are you able to hear us? I think he has
Yes, I can hear you.
Excellent. Wanted to see if we, thank you for that talk. And we wanted to see if we have any questions here from the audience. Does anyone have any questions for Ping or Frank? I do have a question down front.
Hi, oh, nice echo. My question is about IOVA mapping. So what is the granularity of mapping? So do you map like each MBUF page, or do you map whole mempool with single IOVA space? And what is the purpose of this mapping? Do you map it for GPU, or for what purpose?
Yeah, for IOVA mapping, because currently we are leverage external buffer, so that this external buffer finally can be chained together with the M buffer. So for the IOVA side, we will use IOVA to map the allocated external buffer.
Yeah, and the external buffer is, yeah, but you do memcopy as well. So if you do memcopy, so why do you bother with IOVA mapping?
We will not do any. We will not do memory copy for the. Yeah, actually, we have two directions, right? We have another one. First one is TX. Another one is X. And for TX side, we will not do any. We will not do any memory map copy. So we just use the chained buffer to link the video frame with the RTP header linked together. So that, because we want, somehow we need to let NIC understand that this address can be accessed. So we just do IOV mapping to let the NIC understand that this buffer can be used by NIC.
Okay, so how many IOVA mappings do you have for the single 5 megabyte frame? So
yes,
like,
I think it is for the single frame.
Yeah.
One mapping for one frame, but one mapping for one network frame is like 2K frame or 4K, or one mapping for the whole video frame?
The whole video frame.
Whole video frame,
And
okay.
then, then we calculate the IOV offset for each RTP packet in the video.
Okay, thank you.
Yeah.
Is this code upstreamed somewhere, or it's a proprietary one?
This code we plan to upstream that to the community. We are trying several different options. Now it is will be hosted in our Intel repo, and we are trying to connect this link to the DPDK website so that you can find our project in the ecosystem page. Yeah.
Any other questions for Ping or Frank, or both?
Okay, a couple of questions. So your application is running exclusively on Windows?
We can support both Linux and Windows. And I think currently the stability in Linux is much better than Windows. So you can see that we address some issues in Windows side and work together with our DPDK Windows team to cope with some problem. For example, for the 100-page support in Windows side, we found that Windows did not perform very well if we just use 2 Mac 100-page. So that we tend that we need to enable 1 gig 100-page, but not all Windows can support 1 gig 100-page support. So in this case, that we are trying to our library has to run in a specific version of Windows. Besides that, we also realize that, for example, in Windows platform, we do have a KNI feature. Because this is a real workload. It means that the NIC is assigned to DPDK by via file side, but users still need to use this NIC to access, for example, for TCP, IP traffic, for ICMP traffic, kind of things. So we needed to link the non-RTP packet to kernel. In KNI side, we are okay to do that, but in the Windows side, we could not do this job. So you can see that we also present something. We leverage Windows tab device to enable this feature. So there's kind of difference, but in general, we are share the same code base for Windows and Linux.
Okay, and is it possible really for the users to use Linux? I mean, if they want to use some specific codec, is it compatible on Linux?
Codec. What do you mean codec? Actually, for us, we are our current our design is for the production industry. So we are trying to run the standard for ST2110-20. So this is uncompressed video, and another is ST2110-22. It is a compressed video, but this is specific for JPEG XS. So we support that. For codec, it means that they need several frames together to do codec. We did not support that yet. Yeah.
Okay. Okay, there's another question. Just a quick question. You talk about header split.
Yes.
Yeah. I guess you are using the header split based on protocol recognition, which is new in DPDK, because we already had header split in the past, working with offset. Are you able to work with offset, or you need the protocol recognition?
Currently, the simple offset is very simple, right? Currently, we are in our current header split feature, we will leverage RTP to recognize RTP, so that we can do the full protocol parser, not just for offset. In case sometimes IP header will change a bit. So currently we just not use the offset. We will use the protocol analyzer, DDP kind of things.
Okay, got it. Thank you.
Yeah, thanks.
So my guess is that the requirement to support Windows is because the video mixing applications of the production teams would be running on Windows, right? And have you seen any requirements for? I'd imagine people ask for Mac OS as well. Has that happened yet?
Mac, I think we did not receive any requests from customer for Mac. I think the most two popular OS is Linux and Windows, and they also need us to support virtualization.
Any other thoughts, questions, insights for Ping and Frank? If not, then I think that wraps it up. Thank you both for making this possible.
Thanks a lot.
Okay. Thank you.
Yeah, thanks. Bye-bye.